So in this video, I want to go over the force of gravity. But something important to note is that all objects that have mass, for example, this ball has mass and this book has mass. So whenever there are objects that have masses, they feel attractive forces towards each other. So this ball and this book are feeling attractive forces towards each other. This ball and this table are feeling attractive forces towards each other. This book and this earth is feeling attractive forces towards each other. All objects with mass attract each other. And that's not very intuitive, because if we saw this ball and this table standing on a table, we know they wouldn't start moving towards each other. So how can we say they feel attractive forces? We know they're not moving, they're not accelerating towards each other. Well, this force of gravity is very weak. In fact, it's one of the weakest natural forces in the universe. It's a very weak force. So even though they do feel those weak attractive forces due to those gravitational forces, it's so weak that they don't move at all. However, this book, if we were to take this book and to throw it off this table, we know it would accelerate towards the earth. So why does that happen? If we have this book and we were to throw it off the table, why would it accelerate towards the earth? Because again, it's that force of gravity. This book has mass, and the earth has mass, so therefore they feel those attractive forces. And there are a couple variables that affect the strength of that attractive force. And one of them is the mass. And again, so because the earth has such a large mass, its gravitational force is stronger. So that's why they accelerate towards each other. Because both of these objects have such small mass, because the ball and the book have such small masses, they have very weak gravitational forces. But again, just remember that all objects with mass feel attractive forces towards each other. So how do we determine that attractive force? So how do we determine that force due to gravity? Well, it equals big G, which is just a constant, so you can just find this big G in a textbook, multiplied by M1 multiplied by M2 divided by R squared. And this R you can think of as the distance. So if you know these variables, you could feel the attractive force that they feel. For example, let's find the attractive force between this ball and this book. So again, let's say this ball has a mass of 1 kilogram. And let's say this book has a mass of, let's say, 2 kilograms. And let's say they're 1 meter away from each other. Let's say their distance is 1 meter away. So knowing this, what's that attractive force they feel? Well, again, we can just use this equation. We can find that attractive force they feel using this equation. So that force they feel equals big G. And big G is just a constant. It happens to be 6.67 times 10 to the negative 11 multiplied by M1. So this M1 is just the mass of object 1. So let's just define this as object 1. So that's mass is 1 kilogram. Multiplied by M2, so let's say that's this object. So that's 2 kilograms. Divided by the distance they are squared. So they're 2 meters away. We said they're 2 meters away. And again, that distance is squared. So again, G is just a constant. This is the M of one of the objects, and this is the M of the second object. So if we were to just plug this in a formula, it would give us the force in newtons. It would give us the force that they would feel. But we see these terms would cancel, and then again, we would just be left with this, and essentially we would get a force of 6.67 times 10 to the negative 11 newtons, which is a very weak force. So that's why they aren't moving, they aren't accelerating, because they're feeling such a weak attractive force. And also notice this is the force that both objects feel. This object feels a force of 6.6 times 10 to the negative 11 newtons, and this object feels a force of this magnitude in this direction. So they both feel that same force, and notice these are a pair of equal and opposite forces. They're equal in magnitude. They both feel that same magnitude force, but opposite in direction. This one feels that force in this direction, and this one feels the force in this direction. So again, that's what's going on. And again, also remember the Earth also has mass, so that's why all objects with mass fall towards the Earth. For example, if this ball fell off the table, we know this ball would accelerate towards the Earth. Because again, they both have masses, but we know the Earth has a very large mass. So the Earth has a very large mass, so that M1 would be a very large number, so that's why the force is more noticeable, and that's why these objects fall. So let's do a different example. So let's say we had this human. And let's say the human's on Earth. So we know this human feels a force of gravity downward. It feels a force of gravity downward. And again, we know that. We know if we were to, we feel that force. If we were to jump off a cliff, we would accelerate downward because we feel that force of gravity. So what is that force of gravity? Well, again, we probably learned that you can simply solve it by doing mass times g, little g, this little g constant, which is acceleration due to gravity. And we've probably seen this. We've probably seen that's a way you can find this force of gravity. So let's say this person is 70 kilograms. So if we have a 70 kilogram person, and they had this acceleration, this g, of let's be more precise and say 9.8 meters per second squared, what would be the force downward, the force due to gravity? And again, if we were to solve this, we would simply get a force of around 686 newtons. So we know that's the force of gravity that this person feels. They know they constantly feel that force of gravity downward towards the earth, and the magnitude of that force is 686 newtons. And again, we know that. We've probably seen this simplified equation, and then again, we can solve for that gravitational force it feels. However, where do we get that acceleration of 9.8 meters per second squared? Where does that come from? And how do we know this is true? And what's another way we can show the force of gravity that this person feels towards the earth? Well, again, we already explained. The force due to gravity equals big G times m1 times m2 divided by r squared, and r being the distance. So using this equation, we could find that force of gravity that this person feels towards the earth. So in that situation, and again, we know the person has mass, the earth have mass, so we know they're going to feel those attractive forces towards each other. What's the magnitude of that force? Well, again, we can just use this equation. This is a different way to find the magnitude of that force. So again, we know big G, if we want to find that force, we know big G, we already said was about 6.67 times 10 to the negative 11. And again, of course, it has units to cancel this out to give us newtons. But again, so that's big G. M1, let's say M1 is the mass of this person. So again, that's 70 kilograms. So that's M1. And what's M2? M2 would be the mass of the Earth. Because again, these are the two objects that are feeling those forces. So again, these are the two masses. So what's the mass of Earth? Well, it happens to be around 6 times 10 to the 24 kilograms. So that's M2, the mass of the Earth. And then again, now we divide this by the distance between them. And the distance between them, or essentially, really, it's the distance between the center of this person and the center of Earth. And again, so that's what this distance is. It's between the center of mass of the person and the center of mass of Earth. But really, this distance would just be equivalent to the radius of the Earth. Because we know that's essentially the distance. We know this final distance of this half of the person isn't really important. So really, the distance between them would essentially be the radius of Earth. And I know it doesn't look like in this picture, but you can imagine. So really, this radius, this distance between these two people, this r value, the distance between them is really the radius of Earth. And the radius of Earth happens to be 6.37 times 10 to the 6 meters. And again, remember that r, that distance is squared. So now if we were to just plug this in this equation, we would get a force of roughly around 683 newtons. And notice, so this is the force of gravity, the attractive force that this person feels towards Earth. And we already proved that. We already said with this equation that we're probably pretty familiar with, this is a force of gravity this person feels. This is the mass of the person and the acceleration due to gravity, so this is the force. And we see, so this is another way to prove that. And you might wonder, these are a little different. Well, yeah, we're making some simplifications with the mass of Earth. We're not very precise. And then this radius, we're making some simplifications. But you can see we get roughly around this exact same force of gravity. So this is another way you can find that force of gravity. So again, all objects with masses feel those attractive forces. And you can find the magnitude of that attractive force using this equation. And remember, so this is the force that this person feels towards the Earth, 683 newtons. And the same thing, remember, the Earth also feels the same magnitude of that force. This force is the force that both objects feel. So this Earth also feels that force of 683 newtons towards the person. And again, these are equal and opposite forces, equal in magnitude but opposite in direction. And again, so that explains why this person has that kind of acceleration. We already said the acceleration is 9.8 meters per second squared. So we can prove that. We know force equals mass times acceleration. So force divided by mass equals acceleration. And again, we know the force that this person feels is 683 newtons. And we know the mass of the person is 70 kilograms. So now we know the force and the mass, and now we can solve this acceleration. We would get an acceleration of roughly around 9.8 meters per second squared. And again, so that's why we have this, that's where it's partly where this g comes from, and that explains this g, why the acceleration due to gravity is 9.8 meters per second squared. So that's why the person moves towards the Earth. But then you might wonder, why doesn't the Earth move towards the person? We know the person will fall towards the Earth, but why doesn't the Earth move towards the person? Well, again, we could also use this equation to find the acceleration that the Earth would feel. But notice we have the same force. We have the same force of 683 newtons, but now we would have a huge mass. We would have this gigantic mass, this huge mass. So that would give us a very small acceleration, essentially a non-noticeable, non-existent acceleration. So that's why it's such a small acceleration, because we would see a large denominator would give us a very small value. So that there's essentially no acceleration, because again, there's such a small mass. So that explains why the Earth isn't moving towards the person. But the key point is that all objects with mass feel attractive forces towards each other. We can solve that force using this equation.